The demo of my report is synthesis and electronic structure of ultra-thin ferrous selenium film. The iron-based superconductors discovered at 2008 represent the second class of high-temperature superconductors after discovering first-class high-temperature superconductors. Several major classes of the iron-based superconductors was discovered. They can be mainly categorized into the 1-1, uh, 1, 1, 1, 1 to 2, 11, 11, and 3, 2, 5 to 2 system, according to their crystal structure. Similar to the compact superconductors, the iron-based superconductors are positive-dimensional in their crystal structure. One of the interesting iron-based superconductor is ferrum silicon. Some group reports that topology was discovered this superconductor. But as previous speaker said, it is need to understand it more clearly. Also, topological surface state was calculated at the ferrum selenium tellure film at STL substrate. But before understanding superconductivity in topological material, we plan to understand in detail superconductivity in a thin film. Among all of the iron-based superconductors, the ferrum selenium superconductor and its related system have a single crystal structure and specific electronic and physical properties. This crystal structure consists of the ferrum selenium layers that is essential building blocks in the iron-based superconductor. This simple electronic structure is ideal for theoretical and experimental study. We want to understand the difference between superconductivity in volume and in the thin film. For example, why does a pocket disappear at gamma point and appear only at the M point? At the next slide, you can see the Fass diagram of ferrum selenium. When we increase doping by potassium, the critical temperature increase both in volume and in the thin film. Thus, when we increase the Fermi level and increase the number of electrons that can repair the critical temperature increase. As you can see, when we are moving from bulk crystal to ferrum selenium film, pocket hole at the gamma point disappear and appear electron pocket at this point when doping by potassium is increased in the thin film. So we plan to evaluate the dependence of the critical temperature in thin ferrum selenium films. And what is more important, correlation or density of state. And we plan to travel the effect of the substrate terminations on electronic structure. We want to know effect of oxygen vacancies on the charge transfer of ferrum selenium, and to understand effect of non-stoichiometry in ferrum selenium fields, and to study substitution of doping by cognitive. To create ferrum selenium field, I use embryo system of plus 300. You can see the photo of this system and photo of main chamber. This system have high temperature fusion cell for evaporate ferrum and valid selenium source to evaporate selenium. Also, the device have to control the surface state of the sample. Initially, there was problem in the selenium source, which did not allow for spray selenium. This source more complicated than ferrum source. Selenium source have 4 heaters for reservoir, valve, tube, and crater. And the first problem was the incorrect connection of this heater. And the next problem was when I hit valve, the uncontrolled selenium valve increase, and it didn't stop even I close wall and creative. So this it can make good from selenium films. Repairing the source took a lot of time. Now selenium source allow evaporate selenium with speed up to 0.03 angstrom per second. During deposition, I use read to control surface quality. If many defects appears on the surface, the diffraction pattern becomes darker or completely disappear. For creation ferrum selenium films, I use a steel substrate with size 10 by 10 millimeters. Before deposition, I heat the substrate for 30 minutes at temperature 600 degrees. During deposition, temperature of the surface was 400 degrees. Deposition continued 10 minutes. The flux of ferrum was 0.005 angstrom per second, and flux of selenium was 0.03 angstrom per second. To measure it, created samples, I use IBIS express analysis and error of 3000. You can see the photo of this device and the photo of analyzer chamber. This spectrometer allow to make express spectra with an for an energy of 1300 electron volts and IBIS analyzer with radiation of helium lamp. First, I make express analysis of the created from selenium films at 10,000 Fourier. Due to the large spot of radiation, the folder also get into the analyzer area. Thus, we can see the presence of ferrum, iron, selenium, and tantal. The calculation showed that at the film, ferrum, iron, and selenium in the equal quantity. Thus, we can say that this film is in a good quality, and it isn't damaged during the transferring from MV chamber to Aqueous analyzer chamber in vacuum phase with a pressure of about 10 about to the power of -7 millibar. Then I make Aqueous spectra for this sample. I make this spectra from reaction of helium lamp with energy of 40 electron volts. I make spectra with azimuth 0 degrees and 45 degrees. Unfortunately, I can make this spectra only at the room temperature because there's problem with sample. This data is in a good agreement with published data, so I can say that the correct terms and things is in a good quality. We produce by MV relatively thick ferrum-selenium film in stoichiometrically close to the bulk crystal. The ferrum-selenium films are used to moderate vacuum conditions. No oxidation detects after transfer and annealing. Internal conductance of films sufficient to pass measurement, while it's low for electron diffraction. So we plan use neobi-doped STO substrate and low temperature. The thin down film thickness require more complex substrate preparation. Upgrade for MBE with ion sputtering and gas inlays. So I want to thank to Dr. Alexander Fedorov, Professor Bernd Stutner, Dr. Sergei Borisenko, Dr. Alexander Pavlyuk, Dr. Andrei Shapovalov, Ron Spiegel, Vladimir Bezguba, Dr. Evgen Kushlenko, and Andrei Kubarov for this project and for help for its realization. Thank you for attention.
Thank you, Alexander. Do we have questions?
Me.
Sorry, Sasha.
Okay. So I wanted to ask. No, it is the first time when I saw the result, actually, and it is nice that something is dispersed there. The question was about energy, about high energy electron diffraction. Yeah, it is in chamber experiment. And have you seen some spots? You show just for STO surface, yes, but for the evaporated film, have you seen some diffraction pattern?
During yes, thank you for your question. During deposition of the ferrocyan film, the diffraction pattern that didn't change. If I evaporate only ferrum or only selenium, the diffraction pattern change.
So from iron selenium film, it should be different diffraction.
No, the same diffraction.
The same diffraction. Interesting. Okay. And how have you transferred? How have you transferred the sample to the chamber?
So how do you transfer?
Transfer the sample. How you clean the surface?
You can just see. I use manipulator. No, you can see this valve. So I put the sample into this manipulator, close the valve, and disconnect from MBE chamber, and then connect to the Sienta and pumping.
I mean how you get clean surface.
And open valve and put the sample into the chamber. At this case, the vacuum is near 10 to the power of -7. Not.
Okay, my question maybe to Sergey.
It's great that there is some progress in this. There are some first films, and that's really fantastic. And this we should say as the first point. And really should now upgrade the system and to get the thinner films and to go really towards the things which we want to do. This is the first thing. Second thing is it possible to do some films which you could then characterize by means of transport or by other things? So did you discuss this with other people? So just checking whether these films are superconducting, for example.
No,
repeat the remark that it was so nice.
So that it's nice that we have first step that towards thin films, and that's what we wanted to do, to go also towards thin films of selenium on different substrates, and that's let's say the idea. But one thing what you can also do, of course, you characterize it with outbursts and you put emission. That's important. But I could also try to do some films which you could then study by simple resistivity measurement, for example. Did you discuss that with the people, or should I help to make the drawings to other groups here?
But as I know, we didn't plan to measure resistance.
Yeah. But
only
it just gives you another information. So
yes,
it's very simple. Then you extract something like impurity scattering, you can see whether it's a superconductor. So you get some additional information on the quality of these films, but at least if they are thick, and probably these transport measurements should do.
Can you make contacts for transport?
Yeah, later on we can do it.
You can do it outside or do it externally.
External, but it's really cool. In a different way, we can do it before you evaporate the film. But that's something we should also discuss, that we go in this direction. It's just we are learning here and we are doing trying to improve the machines. It's also nice to have that closely connected to the emission, and there is another machine at FeSe which will now be set up similar in a way, but doing the second thing, also trying to get to transport to devices or whatever you want to do later on. That's also nice. So in that sense, we should also discuss this topic.
So I think Pasha was the last question.
My question. I actually finished with questions, but the question actually was more for Sergey, and that I just wondering that Alexander Suvorov, I mean, he is not expert in ARPAs, and it would be interesting that people who measure ARPAs routinely could find some signal there. Better signal, and anyway, I'm impressed that there is something already there. And what Bernd said, that in this case, I guess in the Chinese group who measured it, it is much easier to measure ARPAs and to see superconductivity, how gap opening is opening by ARPAs than by transport. Of course, it's nice if it's possible to realize with transport measurements, but it is much more tricky, I guess. Okay, thank you.
The problem is that this gap in ARPAs measurement was also not straightforward from the previous review. As you know, some gaps open with very apparently at very high temperatures, and then transport shows that this is much lower. So I think when it's combined with the process, if the film is superconducting, you will see them.
But okay, but what you're saying, Sasha, is correct for monolayers. And monolayers transport, that's really very sophisticated. But if you have thick films, and that's what we do at the moment, then characterizing by transport should be straightforward.
I thought that here is not a single layer, but a few layers, or how thick is the sample? I don't know actually.
It's a good question, but I don't know the real thickness of the sample because if we see that show quartz sensor, that is Ferron flux was only 0.005 ampere per second, and if the deposition continued 10 minutes, it must be only near 2 angstrom. But when we make XPS analysis, it shows that the film is the thickness is biggest because we can see the substrate, STO substrate. That's XPS.
Yeah, I'm not expert in this technique, of course, but as far as I understand, the people usually use this read image, just they have oscillations of the structure when they grow layer by layer. So you should reach this possibility to see these oscillations first.
Yes, I know for this oscillation, but this STO substrate isn't at a good quality, and so I can't. No, I can't see this oscillation during the deposition. Maybe at the newly doped STO substrate, I can see this oscillation, but now I can't see it.